just kind of tell me if it beeps. Okay, for those of you watching at home, we have magically put the answer to this problem on the board. F of x equals 1 over x squared plus 1, and we're showing that it's differentiable on R. And when I ask you a question like that, there really is no alternative to just doing it from the definition. Okay, so the definition is the limit as x approaches c of f of x minus f of c over x minus c, and you just plug everything in and just do algebra, really. Factoring and canceling, and you come up with the answer. So there's nothing too deep about that. In fact, I've occasionally been known to ask this kind of question even of my Math 150A students. If it's a simple enough function where the algebra isn't too bad, then it's not a big deal. So this kind of problem is pretty standard. I just thought we'd practice once and remind ourselves of the definition of differentiability one more time. So, okay? You can always check your answer with the rules that we know. If I want you to find a derivative of a more complex function, I probably won't ask you to do it by the definition. I'll say using any properties or rules that you know. And in that case, you can use the chain rule or the quotient rule or whatnot. But if I do say by the definition, then I would want you to, I guess here I didn't. So someone could have come up and just given me the quotient rule, and that would be correct. But if I say by the definition, then you have to do it this way. So, okay, any questions on that? All right, let's do a real easy little follow-up here. Let's show that there exists a C in the open interval 1 to 3 such that f prime of C is equal to negative 1 over 5. So, main thing I'm getting at here is I want to know your reaction. You see a question like that, what does it have to do with? Right, the mean value theorem. You have an interval. You're trying to find the existence of a point in that interval where the derivative is equal to something. So if this doesn't ring bells of mean value theorem, then you need to practice this a bit more, because the mean value theorem is really the main topic that this question is related to, and you should be able to recognize that without any reference to it in the question here. So let's do the mean value theorem. Of course, we already have the function, and we pretty much have the interval. That's why I said this is a pretty easy follow-up. So, and the function is actually differentiable everywhere, so it's continuous everywhere. So all of those assumptions will apply in particular here. So we can go straight to it. By the mean value theorem, there exists a C in the open interval 1, 3, such that f prime of C is equal to the explicit right-hand side of the mean value theorem is just f of 3 minus f of 1 over 3 minus 1. But if you plug in those numbers, f of 1 and f of 3 into the original function and simplify it, you will just get negative 1/5. So that's a real easy one. Okay? Kind of consider that like a warm-up problem. Doesn't involve, there's nothing clever, nothing where you have to do anything tricky. But just wanted to throw something at you out of the blue, literally. And see, sorry, my humor has gone downhill in my old age here. But I try. Anyway, so that's a pretty straightforward one. The third part is a little more work, which is show that f is Riemann integrable on 1 to 3. Okay. So when you see that kind of question, what bells go off?
Looking for a partition.
Pardon me?
Looking for a partition.
Partition of the interval. Okay, and why do you want a partition?
Because I want to find the U and the L.
You want to find the upper sum and the lower sum with respect to that partition and do what with them?
Subtract one from the other.
Okay, subtract them and make it less than epsilon. So you're talking about theorem 6.2. When I say what bells are going off, theorem 6.2 is what you should be thinking of here. So let epsilon greater than 0 be given, And based on kind of our theme of some of our earlier problems, the way we sort of would proceed is we would go over to some scratch work, figure out what the partition should be, and then come back and put it here, right? Okay, so let's do that actually. Let's give ourselves a little more room. I'm going to keep the function there because that's the function we are working with. But let's do some scratch. So how am I going to figure out, to use Theorem 6.2, let me just write it here. By Theorem 6.2, we need to show that there exists a partition from 1 to 3 such that UPF minus LPF is less than epsilon. Any suggestions how I'm going to come up with this partition? How I could try to get there? Like on that last homework assignment, I think I just gave you the partition. I gave you a hint on that yellow homework sheet and said, try this partition, right? But now I'm not giving you a hint. I'm not saying how to create the partition. But we have been talking about a lot today about how to come up with effective partitions, because we have sort of a way now of making any partition that's as fine as we want it to be, right? It's called P sub n. So in that case, we're really just looking for the natural number n that is associated with the partition that we need. But the question is, how do we figure out what the n is if we want to go with that route? I just got to start somewhere.
I think we started the same way that we started the previous ones. We know this is monotone decreasing.
Oh, it's monotone decreasing. That is so not obvious to me. So why is it monotone decreasing?
Our terms are getting smaller on that interval because the bottom's getting bigger.
Okay, so I tell you what, I'm going to suggest one of two things. Either we should draw a graph of the function, just so everybody kind of has a picture of it, or we can go back to part A, where we actually computed the derivative. Remember what we got? I think it was negative 2c. Actually, this is prime of c. Negative 2c over c squared plus 1 squared. Anybody know anything about that?
It's always negative.
Always negative, right? So if it's always negative, well, I should say it's always negative if c is positive, which it will be here, because we're in a positive interval. So as long as we're plugging in a positive number, this is negative. So there's a corollary, I think it's 5.2, that says if the derivative is always negative, then the function is monotone decreasing. Yeah, corollary 5.2. So we could just use that. We could just say that's less than 0 on the interval 1 to 3. And maybe this is helpful anyway, to just draw a picture of this thing. So f of 0 is equal to 1, and then f of 1 is equal to 1/2, and f of 3 is equal to 1/10. Basically, the graph is going to have a horizontal asymptote at the x-axis, and it's going to look the same on this side, although we don't really care about that side. Okay? So this is really where we're focused, and as Dominic pointed out, it is definitely monotone decreasing, right? So it's the usual thing. So if we chop this up into a bunch of equal pieces, right? And we look at, say, UPN of f minus LPN of f. You see, the nice thing about it is you can just pull out the b minus a over n, which in this case is 2 over n, because a is 1 and b is 3. So 2 over n, you can just pull that out, and then all you're left with in the middle is all of the big m's added together, and all of the little m's subtracted. Because the big m's go with the UPF and the little m's go with the LPF. And because it's monotone decreasing, So this is like now the second or third time we've looked at this. Because it's monotone decreasing, you know, for example, big M2, which would be the highest point of the second subinterval, is the same as little m1. And big M3 is the same as little m2, and so on. Big Mn is the same as little n minus 1. So we're just left with m1 minus mn. So this is just 2 over n times capital M1 minus little mn. That is the reverse, by the way, of how it looks for a monotone increasing function. If your function is monotone increasing, what you're going to end up with here is capital Mn minus little m1. It's the same kind of cancellation. You just get one big M minus one little m, but the subscripts are different. You can just replay the video an hour ago when we did the one that was monotone increasing. You saw big Mn minus little m1. Monotone decreasing, it's reversed. It's not a big deal because you can derive it every single time with no problem. All right, and then big M1 is really just f of 1, which is 1/2. And little mn, which is the smallest value of the last subinterval, is just actually little. Isn't that beautiful? You don't actually have to plug in any point that's inside the interior of the partition, which would be ugly to do. Because the points in the inside of the partition, you don't know where they are. They're indexed by these little subintervals of width 2 over m. But we don't ever have to do that. We're just plugging in the left point and the right point. Right? So the little mn is just f of 3, which is 1/10. So minus 1/10. And all of that comes out to, is it just 4 over 5n? 4 over 5n, and we just want that to be less than epsilon, basically. Okay? So over here then, what we do is we just simply say choose a natural number n, right, such that n is greater than 4 over 5 epsilon, I believe. Right? Okay, good. And so then 4 over 5n is less than epsilon. So, UPn of f minus LPn of f is less than epsilon by the scratch. Okay? And so then we're done by theorem 6.2. Again, this is a far cry from actually evaluating the integral. Actually evaluating this integral, this is the antiderivative of this is the arctangent function, so it's not going to come out to any nice number. It's going to be the arctangent of 3 minus the arctangent of 1, according to the fundamental theorem of calculus. And those aren't going to be nice numbers. So, luckily I'm not asking for that here. Just want to know that it's Riemann integrable. Okay? Everybody follow that? Pretty good? Okay. I think we're getting some good practice in today. Got one more example for you, and then we will see if you guys have any questions on the homework. And barring that, we'll call it a day at that point. Okay, so the very last one here, number 8. So it says start off with a less than b. Just take 2 different points, and assume f is diffable on R. Prove. Oh, this is just a repeat of a similar example I did in a previous problem session, but it's been like 2 or 3 weeks. I just thought I'd practice one more time with you. Prove that there exists a C in the open interval AB such that f prime of C is equal to f of b e to the sine of b minus f of a times e to the sine of a all over b minus a times the sine of c, I'm sorry, e to the sine of c. Right? And then minus, somehow you have this subtracted term, f of c times the cosine of c. Okay, so it's a fairly messy looking thing that we're proving here, and we don't even know where c is. It's just somewhere in the interval AB, but we don't We aren't actually finding it to begin with. Okay, does everybody understand the question? F is some function that we don't know. We're getting a fairly messy looking thing here for f prime. And my question, some of you guys were here before, I don't know how well you remember it, but it's from a previous problem class. We did something similar. What general topic do you think this has to do with? What do you think? Mean value theorem? Yeah, I agree. Mean value theorem. So for the mean value theorem, we need a function and we need an interval. Anybody want to tell me what function or interval we're going to use here?
Closed interval AB.
Oh, where you got that from? I really should come up with some easier questions. Okay, so we take the closed interval AB, and now for the function, does anybody have an idea what function we should use? So should we use f of x? We are given a function f. If we use the function f of x, all that we're going to get is, we're just going to get this. That's what the mean value theorem says. That's not what I want, as you can see. So the function f itself is not the right function. So we need to use some other function. So I'm going to change names right away because I don't want to get confused by the name we were using for the original function. So we're going to apply the mean value theorem to a different function g. And Jason, do you have an idea what we might want to take g of x to equal? Not so far? Take a look at what you have here, right? Take a look at what's on the right-hand side of this expression, and think about the mean value theorem, how the formula, of course I had it up there a minute ago. The mean value theorem looks like this, right? You have, a subtraction on top, and the interval on the bottom subtracted, right? And what are you subtracting? You're sort of subtracting the function. So if you look here, and I know we've got this piece over here to deal with too, so I'm not saying it's obvious necessarily what to do. This is actually the hard step. The hard part of this problem is what is the right function to use. But generally, if you look at the form of what you were given here, it might give you an idea. Do you have an idea?
F of x e to the sine of it?
Yeah, see, this is just like f of x e to the sine of x, evaluated at b and a. So let's just try that. Let's take f of x e to the sine of x. Now before I go any further, I will take off points if you don't remind me now that I can apply the mean value theorem to g. So you have to say that because f is differentiable on R, and because e to the sine of x is a composition of differentiable functions, right, on R, that g is, so we really do need to say this, note, g is diffable on R by the chain plus product rules. Because basically g is created by using a product of two functions, one of which is created by using the chain rule. You can use the fact that e to the x is differentiable, sine of x is differentiable, those sorts of things. I know we didn't really officially prove that. In this class we don't really have time to get into the minutia of, on a function by function basis, let's prove that everything is continuous and differentiable and all of that. So you can just go back to your knowledge of calculus for that. But you do need to at least note, see, if you don't write this down, then I feel like you're not thinking through the fact that the mean value theorem has these assumptions on it. So I want to make sure that you put that there. Okay, so can we try the mean value theorem then? Let's just see what it gives us. I mean, you're not going to necessarily see the final answer without doing a little work first, then that's okay. So we don't have to see our way all the way to the solution. So let's just say by the mean value theorem, there exists a C in the interval A to B such that G prime of C, leave a little bit of room here to the left because I'm going to work to the left in a minute. G prime of C is equal to G of B minus G of A all over B minus A. And if I plug in what G of B and G of A are, I'm just going to get f of B e to the sine B minus f of A e to the sine A all over B minus A. Like that. So I kind of have what I want here, but it's not exactly right. It's not exactly right. And besides which, though, this expression, this is not f prime of C, this is g prime of C. Exactly. So what else do you suppose I should do right about now?
Take derivative of G.
Right. I can take the derivative of G. This is my chance to test everybody's product rule and chain rule. Take the derivative of G and put that over here. So I didn't give myself much room, but I'll try. Okay, I'm going to take the derivative of G right here. So it'll be, by the product rule, f prime of x times e to the sine of, actually it's f prime of C times e to the sine of C because we're evaluating at C here. Plus, right, the other part of it is f of C, oh boy, really did myself in. I had plenty of room over there. F of C times e to the sine of C times the cosine of C. Agree? Everybody can read that all right? Sorry, it's a little cramped here. Okay, now here's what I want you to do. Mentally solve for f prime of C. Take this piece here, subtract it over, and then divide by e to the sine of C. Do you see? The e to the sine of C is going to cancel on the last piece. And on the first part, well, you're just going to get an e to the sine C on the bottom here. Okay? So now, I won't show all the work for that. Solve for f prime of C to get the formula. Okay? So that's kind of the idea there. I think this is the one where I was saying you could grab a friend and, make up your own function. Just take f and do something to it. Like here I just combined it like that, but there'd be 10,000 other things you could do. So grab a friend and you each do it and then trade problems and just practice. You can make up your own problems to kind of practice that all you want. It's just a nice application of the mean value theorem. So that is most of everything I had on the problem set. There's a lot of problems today. I had quite a few things to show you. I think that these are in the ballpark of the right difficulty of what I would expect you to be able to do for an in-class test. I'm going to have the same format again. There will be a few places where I ask you to define things or state things. And then typically that might be part of a question, and then there might be a follow-up where you have to do something with that definition. So Taylor's theorem is a good example. State Taylor's theorem and then use it to, approximate the square root of 1.3. That's a nice problem. Riemann integrability, I'm going to probably be asking you to calculate some upper or lower sums. Probably Theorem 6.2 is going to be relevant. Oh, one other thing, forgot to mention. On the review packet, somebody asked me this question yesterday. Somebody asked me, it says norm or mesh of a partition. Sorry, I wanted to go over this really quickly. The norm or the mesh of a partition is denoted this way. It's like an absolute value, double absolute value bar. This is, by definition, the maximum of all of the widths of all of the subintervals. So if you don't use P sub n, if you use a partition that's, you know, chopped up into strange size pieces, right? Then you just go along here and you find the widest one. And that's your delta xi. The reason that that can be kind of handy, let me just show you really quickly here. You don't need to worry about the mesh or the norm if you're using the piece of n partition, which I keep promoting. But see, if you're doing UPF minus LPF, right? So you're doing, you know, delta x1 times big M1 minus little m1 plus delta x2 times, right? You're adding all of these together, right? And you want it to be less than epsilon eventually. Well, one thing you can do is you can replace all of these delta xi's with the mesh of the partition, and then you just have to worry about the m's in here. I think this was kind of my point I was making earlier. There was a problem where I had not made all the delta xi's the same width yet, but you can always increase them to the largest one, and then build your inequality out of that, and then hopefully eventually get less than epsilon from there. Okay, so some people were wondering, it's in the book, it's a very simple idea, it's just the widest subinterval of a partition. But anyway, so UPF minus LPF calculations, you should expect that to be there. So I don't know, I mean, I would guess that 30 to 40% of the midterm is going to be just stating theorems and definitions and maybe proving a couple of the asterisk items, right? So almost half, and then the other half I'm going to give you some problems, you know, that hopefully will be triggered by some of these problem sessions. We haven't done as many group works in class because I've been trying to catch up with my lecture notes, which I'm pretty much caught up now, but there's like only one group work that we did in class, but the problem sessions for sure, there's quite a few good examples there. So I don't know what else to tell you. Just get there early on Wednesday. We'll get there early every day, but especially on Wednesday, so I can give you a little extra time. Seems like that's usually pretty helpful. And you know, it'll be, I hope no big surprise by now. This is already the third time, and so you guys kind of know what my style is with the tests and so on. But there'll be some very easy things on there that, gosh, if you just studied the stuff, even if you didn't understand it, if you just studied it, you should be able to put it down on paper and get it right. And then there probably will be one or two questions, like I usually do, that maybe you haven't quite seen it quite that way before, or something where I would just want to see where you're at in terms of really mastering the material. So I might do, for example, you know, maybe I would give you a function that wasn't monotone but had two pieces, and see if you could think, oh, well, it's going to be, you know, the right-hand endpoint for this part, and then the left-hand endpoint for that part, you know, so something like that. I don't know, just something that maybe a slight twist on something you've seen before, but not something outrageous, right? I'm not going to ask you a big 25-point problem that involves some very trick-oriented thing that you never saw before, right? The more times you've seen me do something, the less I feel like it's a trick, and the more important I think it is. So like this problem right here, we've done a couple of these. If I threw one of these on the exam, you know, I would expect most people to at least have an idea what to do to solve it. But there might be some one or two questions that doesn't look like something you saw before. And I just don't want you to freak out because of it, right? Because if I do ask one or two questions like that, it's not going to burn the whole exam. It's not going to ruin the test for you. I just want to know, you know, who are my people that are really all over it, as opposed to, you can have different levels of mastery, right? You can memorize a bunch of stuff, memorize the definitions and the theorems, and then repeat problems that are similar to what we did before. And that's great. That's, to me, if you can do that, you're already at a very good level. But I'm just looking for like what's up there at the excellent, like really excellent level. I have to ask a couple of questions to kind of probe that a little bit. But it's not going to be, you know, an overwhelming part of the exam. So that's all I'm trying to say. It's the way the other two tests were too.